Okay, well, thank you very much. Thank you very much for inviting me. And to this nice meeting, seeing so many friends. It's really nice. Yeah, the title's long, isn't it? But the thing about the titles, it sounds old, right? It sounds as if I should be giving this talk in German in the 1930s. I mean, so we're at this modern statistical physics meeting, Van der Waals forces, electrolytes. It sounds, how old is this guy? Okay, so let's remind you about Van der Waals interactions across dielectrics. Imagine you take two slabs, glass, mica, something like that. Okay, you have a dielectric constant of your liquid here, you have a difference in dielectric constants, and actually, so what we're interested in is the Van der Waals interaction. So the Van der Waals interaction is just due to dipole fluctuations. So you know, if you look at the interaction between dipoles, you have a 1 over r to the 6th interaction. If you naively integrate this in this configuration, you find this 1 over h cube. Actually, there are lots of dipoles, so there's some interference, and actually, if you look at this limit, I'm interested in this limit where the dielectric constant of the liquid is much larger than the dielectric constant of the material which is around it, so the mica or the glass. So typically, there's a factor of something like 80 to 40 between these things, okay? And if you look in this particular limit, Van der Waals forces, they have a classical component and a quantum component. If you look at the classical component, which is the zero frequency Matsubara part, actually what you find is that it decays like 1 over h cubed, so h is this separation here, and it has some free factor. Beta is 1 over kBt, so it's a thermal effect, it's proportional to kBt. And you can compute this using what's called the Lifshitz theory. And actually, so there are quantum parts as well, which come from the non-zero Matsubara frequencies. But in water, for instance, this thermal component is typically 50%. It's a very large part of the, calculating Van der Waals forces are quite complicated. You have to know all the dielectric properties. You have to do the full Matsubara sum. But if you do this, you're getting about 50% of the Van der Waals interaction. Now, the amazing thing is, if you put salt in here, okay, basically, so now this is my fantastic PowerPoint. The red is the cations, these are the ions, are in the same configuration. Once you put salt in here, this long-range Van der Waals interaction, which was decaying like 1 over h cubed, suddenly becomes screened. And this actually, so if you look at this at large distances, which are typically the distance you'd be interested in, so what you have is you have something called the inverse Debye length, which is given by this 2 rho bar. Rho bar is the average density of your electrolyte. Q is the charge. I'm looking at a monovalent electrolyte system, so the plus charges and the minus charges, this is plus, this is minus Q. So this is called the inverse Debye length. So you have this miraculous screening. So, the Van der Waals pressure is drastically reduced. Okay, well, it perhaps increased because it was negative by the introduction of salt, which is, of course, the inverse of what happens to your blood pressure when you add salt. But anyway, so this is quite a remarkable thing. So a bit of salt changes things. And we all know how it happens, because basically, you have this idea, if this is a positive charge, then, you have negative charges which come and screen these positive charges, and then you have the positive charges move away. And in fact, in terms of the effective interaction between charges, what you find is this Yukawa potential, which is the screen-Coulomb interaction, okay? So this M in particle physics, so this is the inverse Debye length. Particle physicists would call this the mass, okay? So this is how you upset chemical physics referees when you refer to it as the Debye mass. You have referees saying, what is this extravagance? Calling it a mass. It was really, he wrote, what is this extravagance? Okay, so anyway, so let's have a look how this works. So actually, if you take QED, you look at the zero frequency Matsubara, what you have is you have effectively the electrostatic field, and you have a coupling to the charge density with this I beta term. This is why they repel each other, okay? So this is a charge density distribution. This is rho IC. This is coming from the density of electrolytes. So these are my free charges. And of course you have a charge distribution which comes from the dipoles, which is given by the divergence of the dipolar field. Now, a cheap way of deriving a theory is basically say that this dipole field consists of charges, harmonic oscillators, okay? And they have some sort of polarizability, chi. So the first thing that you can do to write down the effective theory, this is how you develop Lifshitz theory, is to, so what you can do is you can say, of course, these dipole degrees of freedom are very rapid, right? They're microscopic, they're moving around very quickly, but your your charges are moving very slowly. So basically what you assume is that you can integrate over the dipole degrees of freedom. They equilibrate instantaneously for a given charge distribution. And so when you do this, you integrate over the dipole, you basically end up, so you can see this term here, squares, you can take a gradient here, and it gives you an effective dielectric constant which is equal to the dielectric constant of the vacuum plus the polarizability field. So this gives you a local dielectric constant. So if you look at this theory here, you know, if you integrate over the field phi, actually, you can see that this has, you know, this is minus div epsilon grad. So actually this will give you the Green's function for a system with dielectric discontinuity. So it actually includes image charges. This is where the image charges come in, okay? So this is your theory. So actually when you look at this, so actually if you're really clever, if you want to do Lifshitz theory, basically you integrate straight over, you do Debye-Huckel theory, because the Lifshitz result comes from Debye-Huckel theory, you integrate over the fluctuations of this density and it gives you an effective field with sort of a renormalite. You have grad phi squared here, and it basically introduces a term which is basically phi squared times the Debye mass squared. And then you do the integral and you find this Green-Casimir interaction. Okay, so that's the sensible way to do it. But actually imagine that I'm going to do the integral over phi before I do the integral over the density fluctuations, okay? Because what I want to do is I want to understand what is coming from the dipole fluctuations and what is coming from the density fluctuations. So if I do it this way, if I don't integrate over the density fluctuations, you know, if I just do this integral, I find the integral in the absence of any charge. So this is actually the van der Waals interaction, right? And you do a Gaussian integral, this is the determinant, and this is the van der Waals partition function in the absence of rho, right? Because if I put rho here, this is 0. And this effective Hamiltonian for the electrolyte ions is basically just this. So this is the charge density of the electrolyte ions, and this is the Green's function, which is given by this formula here. So basically, you know, so what has happened? You've done the integration over the dipole field. It's given you an effective theory for the way in which the ions interact. It's giving you this van der Waals interaction, which is just sitting there doing nothing, right? This is just multiplying, okay? And the way in which the dielectric comes in is, you know, is basically what it's done, it's generated image charges in the dielectric, which gives you the dielectric discontinuity, okay? So this fluctuation term you can do, this is just hanging here. You can work out, you know, you can generate a van der Waals free energy, and if you compute this, the van der Waals force is just minus dF by dH, you find this term. Okay, so that's where it comes from. And you see it has this minus sign. So now this is, you know, this isn't the main, if you look at the ionic contribution, what you can basically do is you can write a theory for the ionic distribution. You can put this entropy term in here. This is the interaction between the ions. And what you do is, in order to get Debye-Huckel theory, you expand the density about the mean density, and you write it in terms of fluctuations. So when you expand in terms of these fluctuations, you get an effective quadratic Hamiltonian, which is given by this. So it's a function of this is n plus and n minus. So this is an entropic term, and this is the term coming from the direct interaction. This is the energy, the electrostatic energy due to the local charge fluctuations. That should be n plus minus n minus, n plus minus n minus. Okay? Now, if you do this integral, what you find is that you get two terms. You get exactly this screened van der Waals interaction, which I wrote down on the first page, but it actually generates a term. You see, because I told you the van der Waals interaction is screened by the electrolyte, and then I showed you that there is this term which is attractive. Okay? So where does the screening come from? Well, the screening comes from a miraculous thing. When you do the integration over the charge fluctuations, you find a repulsive van der Waals interaction, which exactly cancels the attractive one coming from the dipoles. Okay, so this is how you get the effect. And so this was actually noticed in this paper here. This is our take on it. So actually, so from this point of view, if you look at it this way, so if you decide to decompose the overall van der Waals interaction to an ionic and a dipole part, there's a miraculous cancellation. The charge fluctuations of the ions are exactly cancelling out this long-range term just to give you the screen component. Okay? So let's have a look. This seems to be a very delicate thing. So what happens if you apply an electric field parallel to the plates, okay? So basically this was looked at in this paper here. So you just look at exactly the same problem I was looking at, you apply an electric field. So the challenges are you need a dynamical model, you need to generalize the Weihackel theory to out of equilibrium, you need to compute forces out of equilibrium, okay? And so this has just appeared. So this is where we do this. So we're going to use a Brownian model for the ions, we're going to use linearized stochastic density functional theory, and use non-equilibrium formulation for the stress tensor, because it's not trivial to derive the force out of equilibrium. So there are three major technical points. So this is the Brownian dynamics. So we just take Brownian particles. So basically we have a Langevin equation. The force acting on each particle is just an external force plus the interaction due to the other particles. So I have different species types. So that's easy. The dynamics, well, I don't even have to do this, right? Because lots of people have talked about this. We can write down this stochastic density functional theory for the density field. So we have several species, okay? And so this is the effective, so you can write it down with this effective Hamiltonian, okay? So you have this, what looks like a mean field entropy term, but it's not really, and these are the interaction terms. So this is the theory we're going to use. And of course this theory, you know, I have this list when I talk about this, so starting from this, people have developed dynamical density functional theory. You can rederive mode coupling theory, applications to active particle systems, which is perhaps where it is most used, calculate tracer diffusion constants, random matrix theory, electrolyte conductivity, you can revisit and you can improve the Onsager theory, and then I learned yesterday single file diffusion, okay? Okay, so this linearized SDFT. So now if I do the same thing in the context of this Langevin equation, so basically for each species I'm going to write that rho alpha is equal to its average density plus the fluctuation term, and expand in terms of the density fluctuations. The effective linearized SDFT is dn, so basically what you have here is, so it becomes simpler because the mobility, because you're making this expansion, the mobility is now just a constant here. You see this term in the noise, which depended on the full field rho of x, has now been replaced by the average value. So this becomes effectively a Gaussian theory, so it means you can solve things analytically, okay? So what I want to do here is I want to take my Hamiltonian, I expand it, you know, this is the, HF is just the Hamiltonian expanded to quadratic order in the density fluctuations. So it's basically these quadratic terms, n plus squared, n minus squared, plus the interaction. And of course the external force here is F alpha is equal to Q alpha times E, okay? So that's an important thing, you know, and if I just had a single ion of charge Q, if I apply this field, okay, this would introduce a drift into the system, and you would have V would be equal to beta times D times QE, okay? So that would give you the drift of your particles. And this is actually, you know, if you take a Langevin system and you apply an external field, if there are only one type of particles, right, they move all on average with the same velocity, you just go to the frame where they're all moving together and you find equilibrium, right? So the important thing here is that, you know, if I have positive and negative ions, they're moving in different directions, right? So you can't make this Galilean transformation, okay? And the other thing which is subtle in this problem is that you need to impose no flux boundary conditions at the surfaces, because, you know, you're writing down currents, so these ions aren't allowed to go through into the dielectric. And this is not something you have to worry about in equilibrium, right? You know, equilibrium statistical mechanics, you never say, oh, there's no current at the surface, because equilibrium means there is no current, right? You're guaranteed it. So actually this is the this is the form of the linearized SDFT. So you can see it's actually a linear equation, because, so these are just the ionic species, this is my noise term. So you see this is sort of the osmotic term, and this is the term coming from the external field. You see these have different signs, and this is the noise in this linearized approximation. So all you have to do to solve these equations is to, you know, you have, the electrostatic field is given by Poisson's equation, okay? Okay, so this is just the charge density n plus minus n minus, okay? So this system of three equations basically contains all the physics you need to solve, but you have to deal with these boundary conditions. So in the electrolyte, you have the epsilon d phi by dz at the surface is equal to epsilon prime d phi by dz in the slab, right? And actually you can simplify the problem by saying, well, if this epsilon here is much bigger than the epsilon prime here, you can basically impose Neumann boundary conditions. And actually this is important because when you look at the terms in this equation, it means that you can simultaneously have a Neumann boundary condition on the density field and gradient field, okay? Because so you say grad phi is dot n is equal to 0, grad n plus dot n is equal to 0. So you can simultaneously, so you can write down, you can use the same, cos n pi z over h to expand these fields, okay? And if you don't do that, it's very complicated. Actually, if you look at this equation, because you see here, you have a term here, you have a del squared phi gives you n. So actually, if I write down this equation, actually, it looks like a local equation. It's something called the Debye-Falkenhagen equation, which is augmented by this stochastic term. But the problem is the boundary conditions are non-local. You have a non-local boundary condition. But here, so this was one of the things that really blocked us on this problem, because otherwise you have to go to a system of, you have to use, you basically have to work in terms of the eigenfunctions of fourth order differential operator. Things become very complicated, okay? Now the other thing is, how do you compute the forces out of equilibrium? Well, so in this paper, we showed how for a general sort of theory with dissipative dynamics, sort of Langevin dynamics, you can write down the stress tensor. So actually so the way you do it is you write down the body force. So the body force, this is clearly the contribution which is coming from the charge density, right? There's a local body force which is rho, which is the charge density times Q times E. And now if you look at this, the theory for the ions, in this quadratic theory for the ions, you can actually show, we show it in this paper, that you get contributions to the body force which are basically given by something that looks like, rho times the chemical potential, right? The gradient of dH by dN is essentially the chemical ions. And actually, then you play around with that and you can write this body force as well. This external force doesn't really, this doesn't really bother me because it's acting in this direction. What I want to do is to compute the pressure. And so you find that this is given by the divergence of a stress tensor, and this stress tensor is given by this. And so you have this is exactly the Maxwell stress tensor, which comes out of the calculation, but you actually find there's this sort of this term coming from the density fluctuations, and it's very important to keep that term, otherwise you don't get the right answer, okay? So you can't just use the Maxwell stress tensor. So then actually I can compute the force at the lower surface. It's given by this formula, just given by the force per unit area is the difference between the stress at the top and the stress at the bottom. And because I'm calculating a pressure, I have a minus sign here. And so at the end of the calculation, what you find is that the ionic pressure is given by this kBT n plus 0 squared plus n minus 0 squared. And then this is just epsilon times the transverse component of the electric field, which is generated by the ions. So that's it. So now you have everything. So all you have to do, so I've done no calculations so far, I only showed the equations we use. And so actually so symmetric electrolytes, you can generalize this. So what I talk about symmetric electrolyte is a simplified situation where the ions and the anions and the cations have the same diffusion constant, okay? Now actually you can generalize this. This isn't really a constraint, it just makes the formulas look slightly simpler. So actually what you find is that this full force is given by this. So the thing is, when you work this out, this looks horrible, right? But you can actually compute all of these sums, right? And the formula is actually longer than writing down the sum. So, but you can actually explicitly work out these things. It looks horrible. Now, the first thing we have to do, I've written down a dynamical theory. If you go and look at this theory, what you find is that it gives you the Screen-Casimir interaction. And when I say that, it means that the ionic component, so I've taken off I've included the van der Waals interaction in this form, okay? And so basically, when you do it, you have a theory, at E equals 0, you recover the Screen-Casimir interaction. So that's good. I mean, whenever you do something driven, you want to see that you're getting the equilibrium physics right. Now, the thing is, this formula looks horrible, and you're almost embarrassed to show it, but it simplifies enormously in the case of large H, which is the case that you're interested in, okay? So if H is much bigger than this by screening length, you find that it's given by, so you see this universal van der Waals repulsion now, because it doesn't have a minus sign. So this is the disjoining pressure. I've taken off the bulk pressure, right? Because in a system, when the system moves, the bulk pressure doesn't contribute. So this is a repulsive thermal van der Waals component. So it scales like 1 over h cubed. You see that if I put E equal to 0, I get 0 because everything's screened, right? So I'm not putting the screen part. I'm only talking about the long range part, okay? At small fields, you can see that this long-range component switches on as E squared, which you might expect, right? Because it, generically can't depend on E. if it's an analytic function, so you'd expect it to go like E squared. Obviously, if you change the direction of the field, you should get the same force. And actually, I don't know, so you can write this in different ways. You can find, this is a very suggestive way of writing it. You can see that this factor, which is generating the long-range interaction, is given by epsilon E squared over 2 rho kb. So this is a Maxwell pressure, and this is an osmotic pressure. So this is the... if you look at if you take the limit E goes to infinity, right? So you can see that this term here, goes to 0. What you actually find is you can actually find the screening term. If you look at the screening term here, you have this repulsive van der Waals interaction, and you have basically here, this is the screened Casimir effect twice with a factor of 2, with respect to the calculation that we had before. So in equilibrium, there wasn't this term here, I had a 1 here, and actually here the density has been divided by 2. Okay, so, and actually the reason for this, and this is the amazing thing, what happens is that the anions and the cations decouple. As I was saying before, I have 2 frames, I said before, I can decide to move along, on average, you see these cations are moving with this velocity here. So they're moving at the same, they're on the same train, right? So they stay relatively close to each other, and they interact, their charge density fluctuations interact with each other, okay? I'm talking in terms of sort of almost quasi-particles, right? So they're moving together, and the anions, they're moving the same direction, and they're sort of interacting with each other. And so the cationic and anionic charge density fluctuations become independent, okay? Because they don't have time, they're rushing past these guys, so they don't have time to equilibrate with them. So in fact, effectively, they don't interact. So actually you have a theory of electrostatics or electrostatic fluctuations, because they're fluctuations, these ends can be positive and negative, right? There's no net charge here, okay? So everybody says when you do electrostatics, the pluses repel the pluses and the minus repel the minuses. So something a bit subtle is happening here. The charge density fluctuations, that's still true, but the charge density fluctuations aren't interacting with each other. So if I write down this quadratic theory that I showed you at the beginning, right, which is an equilibrium theory, and I say, I'm just going to throw away the interaction between the, so in principle, really, I should have a term minus n plus n minus here, right? The interaction between the positive and the negative charge distribution, but I've thrown it away. So I have a theory for 2 independent charge distributions, right? And so what happens is that when I do the physics of this, when I calculate the partition function, what I'm going to have, each charge fluctuation is going to generate a repulsive Casimir interaction, which would normally cancel the attractive van der Waals interaction, but because I have 2 of them, there's a repulsive van der Waals interaction which is left over, okay? So this is a static calculation for a highly non-equilibrium situation, okay? So, and the extension, if I don't have so this is, so I can look at non-symmetric electrolytes with charges Q plus and Q minus. So overall the system is electroneutral. This guy, the positives can have a diffusion constant D plus, charge Q plus, D minus minus Q minus, and this is the formula that you find. So the expressions are incredibly complicated, but for some reason this long-range component is very simple. The screen component is, will depend on D plus and D minus. So you will see, the effect of non-equilibrium, but this is a sort of indication that this general argument that you have an effective decoupling, so you have an effective static theory due to this decoupling is confirmed. Now the other thing is, now somebody should ask me a question, because I was telling you that if I have 2 types of electrolyte, okay, they move at different charges, so I have 2 independent charge distributions. Now, if I take a mixture of sodium chloride and calcium chloride, right, the sodium ions will move at a certain velocity in the same direction as the calcium ions, but almost certainly the calcium ions, they'll have a lower mobility, but they have a bigger charge. They won't go at the same, go at the same speed. So I can imagine the calcium ions are in their train, the sodium ions are in their train, and the chloride ions are in their train, right? So I have 3 effective charge densities, okay, which should decouple. And if you do the calculation with ionic types with all different bare velocities, so VI is equal to beta diQIE, at large E they should all decouple. So the thermodynamic argument tells me that Ft of H is equal to n minus 1 times zeta 3 over 8 pi h cubed. And actually, I gave this talk in Bordeaux, and there's a guy called Carlos Drummond who does experiments, and he said, okay, we've noticed that when we put AC fields and we change the ionic type, we find these sorts of repulsions. So analyzing the SDFT shows this to be true, and that's my conclusions. Thank you very much for listening to this ancient talk.
Thank you very much.
Yeah, I was just wondering, I thought you gave a purely static integrating out argument for the same effect, is that right?
Yeah, yeah.
And that's okay, why? Because of no flux at the boundaries, you have a zero current state, even in the driven case, is that, did I miss something? Can you just go back?
But you mean, why do I have this? Yeah.
No, how were you able to give,
This. So
yeah.
this, yeah, so basically, so this was my interpretation from the dynamical calculation. This was our interpretation for the dynamical calculation. We noticed that the formula that you get here is the same as if you do this, okay?
I see, as if you drop, you dropped something, you dropped n plus n minus.
So what I'm dropping is the term.
N plus n minus.
Yeah, because when I start, right, I have n plus minus n minus g n plus.
So you dropped n plus n minus.
Yeah, so I dropped the cross term, right?
All right.
Yeah.
Okay.
So that's the decoupling mechanism between the positive. And that would apply, you see, as well if I had different mobilities for my ion. So this is, so this is the argument. So I'm not saying, I don't have a proof of this, right? This is just the interpretation of the results. And as you see, if you go through and you do the algebra, in fact, for n species, which, it's absolutely appalling, but the large H result simplifies, okay? And you find this n minus 1. And the interesting thing is if you take two different species and you give them the same average velocity, you lose a factor of n. So if your calcium ions, right, if you tuned your calcium ions to have exactly the same velocity as your sodium ions, right, by tuning the mobilities, they would move along together and this decoupling would go away. Okay, so for calcium chloride and sodium chloride, if you do this experiment, you should find the long-range repulsion should be 2 times this 1 over h cubed, right? But if you were somehow able to create calcium chloride, calcium that had the same mobility, so it had the same velocity, right? So what needs to be the same is this factor dq. Okay, so if dq is the same, basically you only have one effective charge distribution. And so actually you can show that, so if you go through the algebra of this and you actually set, it's almost impossible to do, right? to have the same average velocity, but this is what comes out, yeah. So this sort of confirms this picture as well. So if so I could write down the theory for calcium chloride and sodium chloride, right?
But so then if you change stochastic process, instead of doing Brownian, you do something else, do you think you have this?
Well, actually, I think this thing, okay, so I would say a lot of this could depend on the model, but actually if you look at this argument, this sort of decoupling argument, right, this suggests that this should be a very robust mechanism. Well, I think it's because, it's, I think there's no time for the correlations to build up. Because you basically, basically everything's happening so quickly here, it just basically sees the charge distribution go past. Actually, when E is big, right, the biggest effect acting on these ions is the electric field, right? It dominates the individual interactions. But that's not quite true because the ions which are moving with the same speed, you can actually go into their frame and their interactions are staying the same. They're not being altered, right? So this is...
Very much.
Okay, thanks.
Long live India and France friendship.